So, we have seen in the last lecture, actually there was last module, right, of the same lecture, that how can we derive the relation between depletion time MOSFET in terms of drain characteristics, transfer characteristics, and we have seen an examples also, right. So, in this particular lecture, part of the same lecture, in this particular module, let us see how we can derive the MOSFET current voltage characteristics, and then let us see how we can use this MOSFET as a very important application, which is your current mirror, alright, current mirror. We will see, it is very interesting application. So, if you see the screen, what you see here is we have a MOSFET here. Now, you can see here this is nothing but N channel. So, we have P type substrate, Now, there is no channel formation initially, but when my VGS is greater than VT, then there will be formation of channel, right. So, if I apply voltage in this manner, that means my gate is positive compared to source, my drain is positive compared to source, right. Then what will happen? That means my electrons will come in this particular region and the channel formation will happen. When VGS is greater than VT, the channel will form. That means, in this particular case, how it looks like? It looks like I have a gate which is connected to a metal, then there is a oxide layer, and then there is another metal. Why? Because this is made up of, this is your channel made up of electrons, right, this one. So, it looks like there are two conducting plates, conducting plate 1, conducting plate 2, separated by insulating layer SiO2. So, what does this reminds us of? This reminds us that this looks similar to a capacitor, right. So, capacitor is what? Two conducting plates separated by dielectric material or air, right. This is why how we define the capacitor. So, here we can see that there is a formation of capacitor when you apply a positive gate voltage and due to which the electrons from the substrate gets attracted towards the gate and forms the channel. This channel forms one plate, the metal through which the contact is taken is forming another plate, while there is an insulator between the two conducting plates. So, this is nothing but your capacitor, Now, if I have the capacitor, then I also know my capacitance is nothing but C equals to K A epsilon naught upon D, right, epsilon naught upon D. This is the formula, that is fine, that we all know, so what. But we also know that current, what is current? Current is nothing but dq by dt, rate of change of charge divided by time, right. Current is rate of change of charge divided by time. Now, what is charge? Charge is nothing but C into V, right. Now, we know this is nothing but epsilon naught, this is formula for C, okay, epsilon naught WL T, V is VGS minus VT. Why VGS minus VT? Because VGS is greater than VT, then only formation of channel will occur. That is why we are writing VGS minus VT, right. That is our minimum voltage or the voltage that is responsible for forming the channels, for forming the channel between source and drain, right. So, again what do we see? I equals to dq by dt, or is delta q by delta t, is nothing but rate of change of charge divided by time. Now, q is nothing but C into V. So, C is nothing but capacitance. So, epsilon into WL by T, right, epsilon naught A by D, right. So, A by D is nothing but, if we can write width into length by T oxide, right, into VGS minus VT. So, let us consider this particular equation, q equals to this value for VDS extremely small. You see here VDS is extremely small, alright, VDS is extremely small, this is the condition, okay guys. Now, what is my T? T is nothing but L by V, right. What is V? V is mu into E. What is mu into E? Mu is free electrons and E is proportional to the voltage and thus distance, right. E is proportional to the voltage and thus distance, right. So, time is nothing but length divided by velocity is nothing but mu into electric field, and this is nothing but free electrons which is mu, and E is proportional to the voltage distance, voltage and thus distance. So, if I substitute this value, then my T would be L square upon L square divided by mu n into VDS. This is my T value, right. So, what I find is my T equals to L square divided by mu n into VDS, L square divided by mu n into VDS, right. Now, if I substitute this value, this value, then what will I have? I will have ID equals to mu n, right, epsilon naught x divided by TOX into W by L into VGS minus VT into VDS, this equation, right. I will get this equation, because now I know what is the value of T, right. So, if I substitute this value, then I will get this particular equation, that is my ID, right, because I know T, I know Q. So, I can find ID, and from ID I know what is the relation between my drain current and my voltage across drain and source, right. Now, if my VDS is high, in this case Q equals to CV, we know mu x W by L TUX, this is okay. VGS minus VT, you see this equation remains same, but instead of VDS we have minus half VDS, because for higher VDS we have to consider a point somewhere in middle of the channel, which is nothing but half times your voltage to voltage applied across source and drain, half times voltage across the source and drain. So, if I substitute this value now, so I now have Q equals to this particular equation, right, which is my equation, let us say x, right, or equation star. So, T equals to, I know this formula here, L square by mu n VDS. So, if I substitute this value, what will happen? ID equals to mu n, this one into W by L VGS minus VT minus half VDS into VDS, right. So, what does this looks like? This looks like nothing but half VDS into VDS, looks like a inverse parabola. So, if I substitute this value of VDS equals to VGS minus VT, what will I have? I will substitute VGS minus VT here, VGS minus VT here. So, I will substitute ID equals to mu n, right, into this particular formula by W by L, right, epsilon naught x upon TOX. When I say this particular formula is epsilon x upon TOX, okay, this one guys, mu n epsilon x W by L VGS minus VT half, instead of VDS I will have write VGS minus VT. So, VGS minus VT into VGS minus VT. When I do this, what I get is I get the formula IDS equals to half times mu n into epsilon x upon TOX. This OX is because of oxide, okay, OX is because of oxide, into W by L VGS minus VT whole square. That means current is independent of VDS. You can see here in my this region IDS, current is independent of VDS, but depends only on VGS, okay. Easy, very easy, right, extremely easy. So, if I now consider, let us see what is channel length modulation. What is channel length modulation? So, I have the channel initially, right, you can see here initially there is a channel like this. Now, if I keep on increasing VDS, I told you, right, if I keep on increasing VDS, then slowly and if I keep on increasing changing the VGS, slowly the channel will start shrinking, channel will start shrinking towards the drain side. So, if initial length is L, length between source and drain is L, then the amount of channel which has been shrunk is delta L, right. Then what will I have? VDS saturation is VGS minus VT, but is equal to VDS minus VD saturation, correct, VDS minus VD saturation. So, let us see here, in this case if I have, if I just magnify this particular portion, what will I see? I see there is a saturation, electric field, x equals to 0, x equals to delta L, this is my drain, my voltage across drain will be VDS is extremely high than VDS saturation, VGS is greater than VT. In this case the inversion charge will happen and my ID formula would be nothing but ID dash equals to length minus original length minus change in the length of the modulation, right, which is my change in the channel modulation into my drain current ID. So, in this particular case when we have to consider the channel length modulation, we have to consider the change in the channel, into the current ID. Okay. So, this is expanded view of cross section near the drain terminal, which is this particular expanded view of this particular terminal like this. Okay, this is what it is here, right, showing channel length modulation, So, if I further substitute the value, what will I have? ID dash equals to Kn by 2. Why Kn by 2? Because I already have formula, sorry. Yeah. So, ID dash equals nothing but Kn by 2 W by L VGS minus VT into 1 plus lambda VDS. This is my formula when I consider the channel length modulation parameter. When I consider the channel length modulation parameter, then I have to, then I get this particular formula for the current, for the drain current. Now, if I want to see what is RO, right, there is a resistance associated with my lambda, right, with my lambda which is my channel length modulation parameter, then it is given by inverse of d ID dash by VDS, right, equals to nothing but Kn by 2, same thing, right, VGS minus VT into lambda whole inverse or 1 by this particular formula. Now, since lambda for small lambda I have nothing but RO will be 1 by lambda ID. Okay. So, most of the time we consider that lambda is small and that is why we can get we can directly use the formula RO equals to 1 upon lambda ID. Alright. It is very easy, very easy. You can see that now here because of the channel length modulation parameters we have the new value of ID dash, right, which is this, and now the RO which is resistance associated with lambda is given by this equation, where for small lambda we can write down RO equals to 1 by lambda ID. So, if I am given a question, if I am given a problem, right, that is more important. Can we solve a problem if we know this? So, you see this particular slide which is this one. So, for ID equals to this value, this equation, if 1 plus lambda VDS, this particular value is 0, then VDS, that is VDS equals to, if this is 0, that means that VDS equals to minus 1 by lambda, right. If this is the case, plot the point of intersection on ID versus VDS plot, mark the triode and saturation region, also write the equation of slope. Okay. So, what is the question? If I am given this equation and I am also given 1 plus lambda VDS equals to 0, and if I am asked to plot the point of intersection on ID versus VDS, that means I am asked that okay, you have ID, you have VDS, why do not you plot a point in for this given condition, also tell us where is saturation region, where is triode region. So, it is very easy, right. See, my VDS equals to minus 1 by lambda, the minus 1 by lambda will be nothing but in this region, right. Now, what we have to do, we have current, right, we have VDS. So, when I increase VDS, I will have this kind of slopes, is it, this kind of plot. When I have this plot, I just connect like this, like this, like this. So, this is my point of intersection, this is my point of intersection. I can say minus VA equals to minus 1 by lambda, right, my point of intersection. Now, this region, this region. So, I plot like this, anything which is here is my triode, this is my saturation region, this is my triode region, this is my saturation region, this is my triode region, right, and my effective RO or output resistance is 1 by lambda ID, is 1 by lambda ID, or I can also write equals to VA by ID, because VA and lambda are related like this, right. So, if I substitute value of lambda, I can get RO equals to VA by ID. Easy, very easy, right, extremely easy. Okay. Okay. If you have any doubt, ask me. Okay, you can ask me through the forum, you can ask me, I will help you out if you have any doubts. Otherwise, the equation is so easy that anyone can solve it, the problem is so easy that anyone can solve it, right, once you know the basics of your MOSFET, basics of your MOSFET, right. So, let us see a very important application of the MOSFET, very important application of MOSFET, right. So, that is the current mirror, that is current mirror. Now, if you can come back to me, I can show you something. Yes. So, let us say you have a mirror, right, you have a mirror. In mirror, when I place a mirror in front of my face, what can I see? What can I see? I can see the image, right. If I put the mirror in front of my face, I see my face, right. That means, the image is replicated on the mirror. I can see the image of my face when I am looking at the mirror, right. Now, if you have gone through this fun worlds, right, they have different kind of mirrors where our body looks like fat, long, short, thin, isn't it. So, that means that mirror can not only show you your actual image, but it also shows you a amplified version of your image or a synced version of your image, correct. That means, the mirror has a capacity to show you different images, of course, of you only, right. So, it is not a movie Harry Potter where you see in the mirror whatever you are afraid of and you can see in the mirror, right. It is not similar to that, but in general when I talk about mirror, what you see is your image, and you can change the magnification of the images using the mirror. So, is there a mirror in electronics, and can we change or magnify the current, right? Is there a mirror in electronics, and can we change, first of all, can we replicate? Second is, if we can replicate, can we change the current? If yes, can we magnify the current? Yes or no? So, we have to see that particular application in the current mirror, alright. So, come back to the screen. It produces the image of the current, right. Current mirror is nothing but it produces the image of the current. It produces an image that is current of a reference current, right. We require a reference current, otherwise how can it produce image? Reference current is highly stable current source, highly stable current source, because here to replicate the current. So, the source should be also stable, and stable source is your highly stable current source. Now, as I said, currents can be scaled up or it can be scaled down. It can be scaled up or it can be scaled down using the current mirror circuit, alright, using the current mirror circuit. So, for this, if you see this particular circuit, what is it? It is a simplest current mirror. Okay. This is called simplest current mirror. So, you can see here the gate is connected to the drain, right. This is MOSFET. There are two MOSFETs, M1 and M2. There is a I reference here, right, and this is IO. So, IO is the mirror of I reference, IO is mirror of I reference, and in this particular case, we can have IO equals to I reference, that is same. We can have IO less than I reference, or we can have IO greater than I reference. We can have three conditions, 1, 2 and 3, right. So, if I draw the circuit, I can also draw like this, I can also draw like this. Now, what I see is I reference, this I reference. What is I reference? I reference, this equation we already know, right. I reference is nothing but K by 2 W by L. Now, because it is 1 M1, so I am saying VGS1 minus VT1 whole square into 1 plus lambda VDS. We have seen this equation just before this slide, right, just before this slide. So, IO would be same thing, just number 2 would be there, because M2 MOSFET 2 is there, right. So, in this particular case, you can see here when I am shorting this one and this gates are shorted, that means the VGS and VGS is equal, that means VGS1 is equals to VGS2, VGS1 will be equal to VGS2, right, and that means that my threshold voltage VT2 should be equals to VT1, VT2 should be equals to VT1. If my VT2 equals to VT1, that means my lambda would be equals to 0, or in another term, if I have VGS2 equals to VGS1, because these are shorted, and VT2 equals to VT1, let us consider first condition, lambda equals to 0. For lambda equals to 0, if I divide the equation number 1 and equation number 2 such that 2 by 1, that means IO by I reference, I will have IO equals to W by L of 2 divided by W by L of 1 into I reference, right. IO equals to W by L of 2 divided by W by L of 1 into I reference. Generally what we will see is L for both transistors are same. Generally we will find that the length for both the transistors are same, and that is why we can write IO equals to W2 by W1 into I reference. Okay. Then we can write IO equals to W2 by W1 into I reference. That is, if I change W1 or if I change W2, then I can see change in current, right, the mirror current. If I keep W1 equals to W2, I will have same current. If I have W1 greater than W2, I will have higher current. If I have W1 less than W2, I will have lower current. That means I have a circuit in which I can change the current, I can have same current, or I can increase or decrease the current, right. That means this circuit is nothing but a mirror circuit. It is a mirror, and that mirror is of a current, and that is why it is a current mirror, alright. But what if so this condition is true when we are considering lambda equals to 0, lambda equal to 0. But what if lambda is not equals to 0? When lambda is not equal to 0, we have this formula, right, we have this formula, that is, by changing W2 and W1, we cannot guarantee that we can have replication of IREF in IO, because now this is the condition that we have to consider, because here lambda is not equals to 0. So, in this particular case what will happen, then there is a error due to this lambda, alright. So, let us see the first error. Okay. Let us see the, in this simplest mirror circuit, if I want to have IO by I reference equals to W2 by W1 into I reference, either I can have lambda equals to 0 or I can have VDS1 equals to VDS2, then only I can have this one gone, and I have this formula which is IO by I reference equals to W by L by W by L. If L is constant, IO by I reference equals to W2 by W1 into I reference. But here if my lambda is not equals to 0 and my VDS1 is not equals to VDS2, then there will be a problem, and problems are, let us see. First one is error due to finite lambda. There is a finite lambda, then what kind of error is there? If VDS2 minus VDS1 increases for lambda, for fixed lambda, error increases, correct. If my VDS1 is VDS2 and VDS1 increases and lambda is fixed, then my error would increase, If I keep VDS minus VDS2 minus VDS1 fixed, if I keep VDS2 minus VDS1 fixed, then for lambda increases, then error again increases, then if my lambda increases, error again increases. So, let us see the another one, error due to variation or mismatch between two transistors, right. If there is a mismatch between two transistors that we have selected for designing the current mirror, what we will see, the threshold voltage of first transistor will not be equal to threshold voltage of second transistor, VT1 will not be equal to VT2, right. If threshold voltages are not equal, then there is a mismatch between the threshold voltages, and that is why for a fixed VT, if reference current increases, error increases, or for fixed reference current, if VT increases, error increases, correct. That is the second error, that is the error number 2. First error was error due to, let us clear the screen, so it is easy for us to understand. First error in the simplest mirror circuit is error due to finite lambda, second error is error due to variation or mismatch between two transistors. The third error is due to layout mismatch. So, if you guys have learned circuit designing, you will use cadence, right, and then you, when you design it, you will see if there is a mismatch in the layout, the design layout, then again there is an error, right. So, for example, if I want W by L of 2 divided by W by L of 1 equals to 2, right, because of the mismatch in layout, I may not get this particular value, and this will also generate in an error, right. So, this all three errors are the errors in the simplest mirror current or simplest current mirror. These errors are the errors in the simplest current mirror. Okay. So, this is just a current mirror action. If you see, right, my M1 and M2, right, if as I increases my VDS, my I reference increases, right. When my I reference increases, my M2 is already in saturation, right, and it will go back towards the current IO, right, because it has to follow, and then this is when it is increasing, this in this one, this is increasing in this direction, this is your current mirror action. So, how we can reduce these three errors? This 1, 2 and 3. Then there is a technique called cascading current mirror, right. So, what we want? We want either our lambda equals to 0 or VDS1, let us say VDS1 should be equals to VDS2, right, because if I see my equation, my IO reference IO by I reference equals to nothing but, right, equals to nothing but W by L of 2 divided by W by L of 1 into 1 plus lambda VDS 2 divided by 1 plus lambda VDS 1. So, to get IO by I reference equals to W 2 by W 1 or IO equals to W 2 by W 1 into I reference, I should have either lambda equals to 0 or VDS 1 equals to VDS 2, right. I should have these two points, but I have nothing in simplest current mirror circuit. I cannot have lambda equals to 0 and VDS 1 equals to VDS 2, particularly when your VDS 1 is not equals to VDS 2, particularly when your lambda is not equals to 0, particularly when your lambda is not equals to 0, right. Then you cannot have this particular value where your IO by I reference will be W by L of 2 divided by W by L of 1. This we cannot have, right, this we cannot have. So, what can we do? We can use cascaded current mirror, cascaded current mirror. In cascaded current mirror, what we use? We use 4 MOSFETs, M1, M2, M3, M4. We use 4 MOSFETs and we connect the drain to the gate like this drain to the gate like this, and then these gates are connected, this one is connected like this. M3 and M4 are in series, M2 and M4 are also in cascaded condition, alright. Now, you can see here that if I have VDS 1 equals to VDS 2, that means this VDS 2 and 1 and 2 here. If my VDS 1 equals to VDS 2, my error would be 0. So, cascaded current mirror were studied by 2 different groups. One is Razavi, where he proposes that if IO is not equals to I reference, if lambda equals to 0, let us consider this particular condition. Okay. IO is not equals to I reference because if lambda equals to 0, that is same current flows in M1 and M3, same current flows in M1 and M3, assuming W by L and VT are same, VGS 3 equals to VGS 1, correct. So, what he says is that if I consider my M1 and M3, alright, M3 and M1, alright, and I assume that my threshold voltage of M3 W by L and threshold voltage of M3 and M1 is same, right. Threshold voltage and W by L ratio are same, or threshold voltage is same and W by L ratio is same of what? M1 and M3. In this case, since VGS 3, you see VGS 3, right, is equals to VGS 1 or VGS 3 equal to VGS 1, since gates of M1 and M2 are shorted, right, since M1 and M2 are shorted, that means that VGS 2 should be equals to VGS 1, right, and the same, since same current flows in M4 and M2, that means that VGS 2 equals to VGS 4, right. So, first is when VT equals to VT and W by L are same, that means that VGS 3 equals to VGS 1 because my VT and W by L are same, right. W by L are same. So, VGS 3 equals to VGS 1, alright. Now, if VGS 3 equals to VGS 1, since the gates for M1 and M2 are shorted, that means that VGS 2 will be equals to VGS 1. Now, since same current flows in M4 and M2, that means that VGS4 is equals to VGS2. If this is the condition, that means my VDS2 would be equal to VDS1. My VDS2 would be equal to VDS1, and here we have considered lambda equals to 0. Then if this is the condition, what will happen? My error will be not there. Why? Because my equation IO by I reference, right? You have seen this equation, correct? This one. So, IO by I reference is nothing but W by L of 2, W by L of 1, 1 plus lambda VDS of 2, 1 plus lambda VDS of 1, right. VDS2 equals to VDS1, condition is satisfied. Lambda equals to 0, we have assumed here. That means our error would be 0, So, if lambda is not equals to 0, in that case what will happen? If lambda is not equals to 0, in that case what will happen? In that case we will see here that VDS1 equals to VDS2 implies IO equals to I reference, right. But the catch is, lambda for M3 and M4 is 0, but for M1 and M2 is not equals to 0. So, what we say is, for if lambda is not equals to 0, then VDS1 equals to VDS2 implies IO equals to I reference. So, both this condition is okay to remove the error, but here what we are assuming is that lambda for M3 and M4 is 0, M3 and M4 lambda equals to 0, while lambda for M1 and M2 is not equals to 0. This is not correct, right. Either lambda for all the transistors should be 0, or lambda for all the transistors should not be equal to 0. So, this is a catch when we calculate the that whether the error is not there using the method proposed by Razavi, all right. So, what we can do? We can see another method that is proposed by Allen and Hallberg. So, here what they propose is, let us consider that the cascoding M3 on M1, this if I cascode M3 on M1, that means my R out increases, right, because I am cascoding M3 on N1, right. See, if I cascode this MOSFET M3 on M1, my R out would increase, right, that is sure. Now, what is my formula for R out? We have seen R out equals to 1 by lambda into IO, right. R out equals to 1 by lambda effective into IO, correct. So, if that is the formula, lambda effective would be nothing but 1 by R out into IO. Now, R out is what? R out is extremely high, that means my lambda effective would be close to 0. So, even there is a finite mismatch between VDS1 or VDSA and VDSB, since lambda effective equals to 0, my error is less, and my IO will be equals to I reference. You got it? Very easy, right, super easy, and this is, it makes sense when we discuss like this. When we discuss in terms of what Allen and Hallberg is proposing, it makes more sense, because here if I cascade M4 on M3, M4 on M2 or M3 on M1, my R out would increase. Since my R out is related to my lambda in this particular fashion, which is inversely proportional, I can see that increasing in R out will decrease in lambda, and that is why my overall error would decrease, even there is a finite mismatch between my VDSA and VDSB. That means Allen and Hallberg proposed that by using the cascaded kind of current mirror, we can reduce the errors generated in the simplest mirror current in the simplest current mirror circuits, right. The errors in the simplest current mirror circuits can be reduced by using cascaded current mirrors, all right. So, this is end of application of current mirror. I just wanted to show you to you that how you can use MOSFET for a particular application, that is a current mirror, that is a current mirror. Let us go to the another point, and that is your complementary metal oxide semiconductor, right, and we will not go too much detail into this, but we will just see how the CMOS can be used as an inverter. Okay. So, CMOS stands for complementary metal oxide semiconductor. CMOS technology is one of the most popular technology in the computer chip design industry and broadly used today to form integrated circuits. Okay. So, whenever you see any integrated circuits, in most of the cases you will find CMOS, right. Today's computer memories, CPUs, cell phones make use this technology due to several key advantages. This technology make use of both P and N channel semiconductor devices. When you connect P channel and N channel MOSFETs, you will get complementary metal oxide semiconductor. Now, the main advantage of CMOS over NMOS or bipolar transistor is much smaller power dissipation, and that is very important because we are going to reduce the number of components or increase the number of components on a single wafer, right. Reduce the size of component and increase the number of component on the single wafer. When you want to do that, when you want to reduce the size, the power consumption also get subsequently reduced. That is possible by using the CMOS technology compared to bipolar transistor or NMOS technology. Power is only dissipated in case the circuit actually switches. So, power is not dissipated if circuit is ideal, only when it switches from one state to another state the power is dissipated. This allows integrating more CMOS gates on an IC than in NMOS or bipolar technology, resulting in a better performance, right, because only when it operates then only the power is dissipated, and that is why you can have more gates compared to bipolar or NMOS. Complementary metal oxide semiconductor transistor consists of P channel MOSFET and N channel MOSFET, okay, P channel MOSFET and N channel MOSFET. So, you can see here we have P channel MOSFETs and N channel MOSFET. So, if you see as a NOT gate, if I want to use this as a NOT gate, that is my CMOS as a NOT gate, right. NOT gate, you know, if I apply 1 my output is 0, if I apply 0 my output is 1, right. How can I operate that? You see here, see there is a switch, right, there is a switch. So, you see here that if VDD is my voltage, this is ground. So, if I have x equals to 1, this will be open, my output would be 0. If my x equals to 0, this closes and my output would be 1. So, this is how I can see the change. Let us see here in this particular circuit, when I apply Vx equals to 1, right, what happens? Vx equals to 1, my this is PMOS, right, this is PMOS. So, this will not conduct, and that is why this will be my transistor T1 would be off and T2 would be on, and that means that my output voltage will be nothing but 0. But if I have reverse of this, that means that if I apply Vx equals to 0, then what will happen? This will conduct, right, this will not conduct. So, that means this is my T2 would be off, T1 would be on, and that is why my output will be 1. Now, what is this? This is nothing but PMOS and NMOS connected together, PMOS and NMOS connected in series, right. So, if this is the, in this way, if I have the circuit, I can use it as a NOT gate, right. So, in CMOS technology, both N type and P type transistor are used to design logic functions. The same signal which turns on a transistor of one type is used to turn off the transistor of another type. You can see, right, if I apply 1, this is off while this is on, right. See, the same signal which turns on one transistor will turn off the another one, will turn off the another transistor. This characteristic allow the design of logic gates using only simple switches without need of pull up resistors, right. So, when we do not require pull up resistors here, in CMOS logic gates a collection of n type MOSFETs is arranged in a pull down network between output and low voltage supply, right. Instead of load resistor of NMOS logic gates, CMOS logic gates have a collection of P type MOSFETs in a pull up network between output and higher voltage, right. Here we, instead of using the load resistors as a pull up resistors, we can use P type MOSFET as a part of pull up network, right. So, here this is how the CMOS is designed, it is how it is connected, and we will not go too much detail into CMOS. We have to just understand that if you are given a CMOS and if you are asked to form a NOT gate, you can use a NOT gate by just attaching PMOS to NMOS, and the advantage of CMOS is at one time only it will only dissipate the power when it is in the on state, when it switches between the on state and off state, otherwise it will not dissipate the power. That is the advantage of CMOS over the bipolar transistors, Okay. So, with this what we have seen, we had in the today's module, what we have seen, we have seen P channel, we have seen depletion type MOSFET, we have seen the transfer characteristics, then we have also seen the application of the current mirror, and how what are the errors in the simplest current mirror. Then we have seen that can we reduce the error in the current mirrors that are there, and then what was the proposed idea? The proposed idea is that we can use a cascaded current mirror to reduce the errors in the simplest current mirror. This current mirror were proposed by two groups, one is from Razavi, another is from Allen and Hallberg, and we found that in the Razavi's model we had to assume two transistor lambda equals to 0, another two transistor lambda is not equals to 0, which will not work. That is why we have to consider Allen and Hallberg, where it makes sense that if you attach two transistors in the fashion in a cascaded current mirror, then your R out will increase, and since R out is inversely proportional to your lambda, that is why your lambda will decrease if R out is increased. That means your error would be close to 0, even there is a finite difference between your voltage generated across the transistors I reference and IO. That means that this particular model, which is proposed by Allen and Hallberg, makes more sense to understand how the errors are reduced in the simplest current mirror, right. Now, in the next class we will start understanding what are the operational amplifiers and what are the characteristics of the operational amplifier. Alright. So, I will see you in the next class, and we will start understanding the operation amplifiers, which is also called the op amps, So, look at the things that I have taught you today. If you have any questions, feel free to ask me. The course is designed in such a way that you get the understanding and the idea of how the op amps, how the MOSFETs and ICs are fabricated. At the same time we will touch the base of a few of the topics, so that it helps you to cover most of the topics in your analog circuit domain. There is another course which is advanced version than what I am teaching right now, but what I thought is, let us start with something which is more to which covers not only basics, but it also covers the experiment point of view. So, we will also see lot of experiments as a part of this particular course. Okay. So, I will finish this module at this particular point, and I will see you in the next class. Till then, you take care. Bye.